Okay. So it's quickly becoming apparent to me that this book, Quantum Computing Since Democritus, is one of those all-time books. It's one of those books that's for all time. So we're just going to start from the beginning. And because last time I think I went over some Busy Beaver stuff, the proof for why the halting problem is undecidable, and maybe some other stuff. But let's just start from the beginning. Okay. Atoms and the void. I would rather discover a single cause than become king of the Persians. So why Democritus? First of all, who was he? He was an ancient Greek dude born around 450 in this podunk town, where people from Athens said that even the air causes stupidity. He's called a pre-Socratic, even though he's actually a contemporary of Socrates. That gives you a sense of how important he's considered. Yeah, the pre-Socratics. Maybe stick him somewhere in the first week of class. He was too shy to introduce himself to Socrates. Democritus thought the whole universe is composed of atoms in a void, constantly moving around according to determinate, understandable laws. These atoms can hit each other and bounce off, or they can stick together to make bigger things. They have different sizes, weights, and shapes. It's got to be amazing to be like a philosopher from this time, because it's like they don't know anything, and they have hardly the tools to test things. Color and taste are not intrinsic, but emerge out of the interaction of many atoms. For the atoms that made up the ocean were intrinsically blue, how could they form the white froth on waves? This is 400 BC, so we're batting pretty well. Suppose we have an apple, and suppose the apple is made not from atoms but continuous hard stuff. And suppose we take a knife and slice the apple into two pieces. It's clear that the points on one side go into the first piece and the points on the other go into the second piece. But what about the points exactly on the boundary? Do they disappear? Do they get duplicated? Is the symmetry broken? None of these possibilities seem particularly elegant. Ugh. There's a debate raging even today between atomists and anti-atomists. At issue in this debate is whether space and time themselves are made up of indivisible atoms. At the Planck scale of 10 to the minus 33 centimeters, or 10 to the minus 43 seconds. Once again, physicists have very little experimental evidence to go on, and are basically in the same situation that Democritus was in 2,400 years ago. Am I quiet? Hello? 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 Am I quiet? No, I don't know why. Hello? There we go. If you want an ignorant, uninformed layperson's opinion, my money is on the atomist side. And the arguments I'd use are not entirely different from the ones Democritus used. They hinge mostly on inherent mathematical difficulties with the continuum. One passage of Democritus that does survive is a dialogue between the intellect and the senses. The intellect starts out by saying, by convention there is sweetness, by convention bitterness, by convention color, in reality only atoms in the void. For me, this single line already puts Democritus shoulder to shoulder with Plato, Aristotle, and any other ancient philosophers you care to name. It would be hard to give a more accurate one-sentence summary of the entire scientific worldview that would develop 2,000 years later. I mean, that's sweet, bro. That's freaking sweet. The senses respond by saying, "Foolish intellect, do you seek to overthrow us while it is from us that you take your evidence?" It's crazy. Alright. I came across this dialogue in a book by Schrodinger. By the way, guys, Schrodinger, not such a good guy. Ooh. Sorry, fellas. He's not that good of a guy. Schrodinger. See, we're inching towards the quantum computing in the book title. We're going to get there. Don't worry about it. But why would Schrodinger be interested in this dialogue? Well, Schrodinger was interested in a lot of things. He was not an intellectual monogamist, nor really any kind of monogamist. Not even that. Anyways. But one reason he might have been interested is he was one of the originators of quantum mechanics. In my opinion, the most surprising discovery of the 20th century, relativity being a close second, and the theory that adds a whole new angle to the millennial-old debate between the intellect and the senses, even if it fails to resolve it. Here's the thing. For any isolated region of the universe that you want to consider, quantum mechanics describes the evolution in time of the state of that region, which we represent as a linear combination, a superposition of all the possible configurations of elementary particles in that region. So this is a bizarre picture of reality, where a given particle is not here, not there, but in some sort of weighted sum of over all the places it could be. But it works, and as we know, it does pretty well at describing the atoms in the void that Democritus talked about. The part where it maybe doesn't do so well is the "from us you take your evidence" part. What's the problem? If you take quantum mechanics seriously, you yourself ought to be in a superposition of different places at once. After all, you're made of elementary particles too, right? In particular, suppose you measure a particle that's in a superposition between two locations, A and B. Then the most naive, straightforward reading of quantum mechanics would predict that the universe itself should split into two branches. One where the particle is at A, and you see it at A. One where the particle is at B and you see it at B. My bad, guys. That's never happened to me before. So what do you think? Do you split into several copies of yourself every time you look at something? I don't feel like I do. You might wonder how such a crazy theory could be useful to physicists, even at the crassest level. How could it even make predictions if it essentially says that everything that could happen does? Well, the thing I didn't tell you is there's a separate rule for what happens when you make a measurement. A rule that's tacked on, external to the equations themselves. That rule says, essentially, that the act of looking at a particle forces it to make up its mind about where it wants to be, and that the particle makes its choice probabilistically. And the rule tells you exactly how to calculate the probabilities. Of course, it's been spectacularly well confirmed. But here's the problem. As the universe is chugging along, doing its thing, how are we supposed to know when to apply this measurement rule and when not to? What counts as a measurement? That's really what I want to know. The laws of physics aren't supposed to say such and such happens until someone looks, and then a completely different thing happens. Physical laws are supposed to be universal. They're supposed to describe human beings the same way they describe supernovas and quasars. All examples are just vast clumps of particles interacting according to simple rules. So from a physics perspective, things would be so much cleaner if we could dispense with this measurement business entirely. Then we could say in a more sophisticated update of Democritus, there's nothing but atoms in the void evolving in quantum superposition. But wait, if we're not here making nosy measurements, wrecking the pristine beauty of quantum mechanics, then how did we, whatever that means, ever get the evidence in the first place that quantum mechanics is true? How did we ever come to believe in this theory that seems so uncomfortable with the fact of our own existence? How did we ever come to believe in this theory that seems so uncomfortable with the fact of our own existence? So that's the modern version of Democritus, the Democritus dilemma. Democritus? I don't fucking care. And And physicists and philosophers have been arguing about it for almost 100 years, and in this book, we're not going to solve it. The other thing I'm not going to do in this book is try and sell you on some favorite interpretation of quantum mechanics. You're free to believe whatever interpretation your conscience dictates. What's my own view? Well, I agree with every interpretation to the extent that it says there's a problem, and disagree with every interpretation to the extent that it claims to solve the problem. That's fucking cool, man. See, just like we can classify religions as monotheistic and polytheistic, we can classify interpretations of quantum mechanics by where they come down to on the putting yourself in coherent superposition issue. On the one side, we got the interpretationists that enthusiastically sweep the issue under the rug. Copenhagen and its Bayesian and epistemic grandchildren. In these interpretations, you've got your quantum system, you've got your measuring device, and there's a line in between them. Sure, the line can shift from one experiment to the next, but for any given experiment, it's got to be somewhere. I don't quite know what this means. In principle, you can even imagine you're putting other people on the quantum side, but you yourself are always on the classical side. Why? Because a quantum state, that would be really crazy if, like, I kind of hate all of this stuff too, in a sense, because it's like, are we really going to get anywhere? But it would be very interesting if each individual person is sort of master of their own universe. They are the sole true one measuring device that exists on the planet. I think you could probably disprove it. I don't know if you could prove it, whatever. But interesting. This whole stuff is very interesting. Why? Because a quantum state is just a representation of your knowledge. It's so bright. I wish I could, like... Is there a way to read this PDF in, like, inverted colors? Anyways. But what if you want to apply quantum mechanics to the whole universe, including yourself? The answer in the epistemic type interpretations whether or not the observer yourself can be treated as part of a quantum system. In interpretations like the Copenhagen I don't even know what this means. The quantum state is a state of knowledge and not a physical entity. Wait, what? In these views, the quantum state represents the information or beliefs of an observer about a system? That's a very interesting thing, actually. I never considered that. You're not allowed to ask a question like this. Okay. Do not ask that question, you naughty boy. But what if you want to apply... Oh, wait, we already read that. Now, to hot-headed problem solvers like ourselves, this might seem like a big dispute over words. Why bother? But as David Deutsch pointed out, we can conceive of experiments In this view, philosophers sit in their armchair waiting for something surprising to happen in science, like quantum mechanics, Bell inequality, Gödel's theorem. Well, on its face, that seems sort of boring, but as you get more accustomed to this sort of work, I think what you'll find is it's still boring. Personally, I'm interested in results. I'm finding solutions to non-trivial, well-defined, open problems. So what's the role of philosophy in that? I want to suggest a more exalted role than intellectual janitor. Philosophy can be a scout. It can be an explorer mapping out intellectual terrain for science to later move in on and build condominiums on or whatever. Not every branch of science was scouted out ahead of time by philosophy, but some were. And in recent history, I think quantum computing is really the poster child here. It's fine to tell people to shut up and calculate, but the question is, what should they calculate? At least in quantum computing, which is my field, the sorts of things we like to calculate, capacities of quantum channels, error probabilities on quantum algorithms, are things that people would never have thought to calculate if not for philosophy. Alright, here we go. This is what I wanted to get to. I wanted to get to some fucking math. Yeah, all this philosophical nonsensory is not my thing. I'm just kidding. I love it. I'm just kidding. I hate it. You decide. Alright. Sorry, so set theory. Guys, set theory. I don't know anything about this. Here we're going to talk about sets. What will these sets contain? Other sets. What does he do? Nope, that's incidental. Other sets. Like a bunch of cardboard boxes. Yeah. Okay. Gottlob Frege. Before we talk about sets, we need a language for talking about sets. The language that Frege, Russell, and others developed is called first-order logic. It includes Boolean connectives, Okay. Alright, first order logic is basically Boolean connectives, the equal sign, parentheses, variables, predicates, quantifiers. I'm told that the physicists have trouble with these. Hey, I'm just ribbing you. If you haven't seen this way of thinking before, then you haven't seen it. But maybe for the benefit of the physicists, let's go over the basic rules of logic. Alright. The rules of first order logic. Huh. Okay. Yeah, I guess that makes sense. I wonder about. I always like to question this stuff. It would be interesting. What does the math look like where for some reason either it's like the usage of a symbol or something mutates it in a way, and so you can never say x equals x. I don't know. Just a thought. There's a lot in here. Like, what does unrestricted mean? And quantifier rules. Okay, that all makes sense. So, for example, here are the piano axioms for the non-negative integers written in first-order logic. Ah, interesting. Okay. Right. So let's just say dot. PA axioms written there exists a z such that for all x, Sx is not equal to z. That's the first one. Okay, those are the piano axioms. I mean, that's so basic, but it is cool. And just for historical context, let's look up this. What the hell? Doo-doo. This guy was crazy, bro. So, late 1800s, they started to do this stuff. I mean, just think about all the stuff that was going on in the world, and people were still just, like, living their lives, being like, let's just do some math. I don't fucking care. The non-negative integers themselves are called a model for the axioms. Yes. Yes. Okay, this is what I was getting so confused about. It's because I was reading this, like, late at night, and I was, like, not getting it. But this is what I was trying to get at. Okay, because I did not understand this model stuff. What does that mean? The word model just means any collection of objects and functions whose means any collection of objects and functions of those objects that satisfies the axioms. Interestingly, though, just as the axioms of group theory can be satisfied by many different groups, so too the non-negative numbers are not the only model for the piano axioms. For example, you should check that you can get another valid model by adding extra made-up integers. But like, do you have to associate this z with 0? I think not. The idea behind non-standard models is that the Peano axioms don't force you to only have... Oh, wait, but why do you have to have an infinite number of them? Am I right about this, guys? I feel like I am. Where's the statement of them?